Hello, welcome to the Tech Talk, Resource-Aware Programming. It's my pleasure to introduce Walid Taha, who I met at Rice University while I was giving a talk, and now he gets to do the same, except at Google, which I think is a pretty cool place to give talks. Anyway, no further ado, here's Walid.
Cool. Thank you very much, Chris. It's a pleasure to be here today, and the goal is to tell you all about the interesting research in programming languages that we're doing at Rice. And I'll avoid getting into technical details and theorems and formalisms and so on, and focus on using various examples and languages that we've built, and intuitions and motivation from the kinds of problems that we'd like to see our languages being used to solve. So to get started, I'd like to say that one of the key things to building better programming languages is to design abstractions that would help us build the programs that we want to write. Abstractions like arrays, functions, objects, modules, and so on, all of these are examples of things that we've seen before in different application domains like high-performance computing or databases, for example, where they've proven successful. All right. And there are a lot of standard examples of these abstractions that we know pretty well. How do they help? In a lot of cases, they do a very simple thing, which is to make our programs shorter and more manageable. Often, they also make it easier to reuse, so that when we've solved something, a particular problem before, it's easy to reuse the solution to solve a new problem that we've seen. And if they're designed carefully, then they can also help us verify and reason about the correctness of our programs. Okay. And in particular, reasoning is something that we're very interested in. And when we're able to do that, what we get at the end of the day is a guarantee about our program, often through the language that we've created or the type system in particular. We get a guarantee about our program, and the guarantee says a specific bad thing won't happen at runtime. Okay, so you've built this program, and it looks like it's supposed to be doing a certain thing, but we're also interested in knowing that there are other bad things that it's not going to do. Okay, of course, ultimately, if we take verification all the way, then we go the next step, and we'd be sure that it's doing what we wanted it to do. Okay, but a very practical thing is to have at least guarantees about certain bad things not happening. And here we're interested in things, classic things like buffer overruns or runtime errors and so on. Okay, and there's very intricate interplay between the design of abstractions and what we can do in terms of reasoning about our programs afterwards. All right, so the last slide is supposed to be motivation for the design abstractions that we get in high-level programming languages. High-level programming languages, to me, are things like OCaml, ML, and Haskell, and all these, very high-level programming languages that we know about. Now, if we go to the real world and look at the kinds of programs that people are writing today, then we'll find that, well, what do they look like? They look like the controllers that run inside our car. All kinds of medical applications and health services applications, robotics applications. They run important. They have very important control software that determines what function the rest of this metal does, and the same thing for defense applications. So, what languages do people use to write these pieces of software? There are things like C and C++ for the most part, and if we're very interested in performance, if there are big computational components of the system, then we might find that they're written in Fortran. These are actually, even though 40 or 30 years ago these were high-level languages, today they're not what we would consider high-level languages based on the new innovations that we've seen over the last 20 or 30 years. So why is it the case that for a lot of the applications and the software that is being written today, we don't see the high-level languages being used? So my thesis here is that basically, at the same time that we use these more advanced abstractions, we're also giving up control over fairly important low-level details. And in a lot of cases, especially for embedded and real-time systems, a lot of times the benefits that we get, there are a lot of benefits that we get from the high-level abstractions, but the programmer that's responsible for building the system at the end of the day can't really give up the control over the low-level resources, because that programmer or system designer is the person that's responsible for achieving these real-time guarantees or the various performance characteristics that the system must have. Okay? So there are a lot of examples of abstractions that we could use to illustrate this point, the simplest one is maybe automatic memory management. Okay. Automatic memory management allows us to think of dynamic data structures at a higher level than the model where we allocate data explicitly and then deallocate it at the end of the day. And we get this huge advantage with dynamic memory management of safety, because if we have only allocate operations and no explicit deallocate operations, then we don't have to worry about dangling pointers, which are a big safety problem in languages that don't have dynamic memory management. So you get a very nice abstraction from dynamic memory management. At the same time, this means that we relinquish control over when things get allocated and also when things get deallocated. In addition, because the system has to do more work for us and we don't necessarily know when this work will be done, we may be doing a critical computation that needs to be done quickly for this particular application, and then the garbage collector must run, and suddenly we have no idea how long it's going to take for this computation to finish. Okay. So this is just one example of many instances where we care not only about the functionality or input-output behavior of our program in terms of the standard input-output behavior, but we care also about the resources that are being consumed, the basic resources being time and space needed for the computation. But we can imagine all kinds of other notions of resources that depend on the particular kind of problem that we're solving using the software artifact that we're trying to build. Okay, so the question that we're interested in, what are the abstractions that can be used to allow people to build the programs that they want to build and at the same time get guarantees about resources of this form? So the goal of the research, of our research, is basically to be able to produce languages that are as expressive as possible to the programmer, so that we could still structure our problems as clearly as possible and reuse the solutions that we have before. At the same time, just side by side to this expressivity, we want to have guarantees that are as strong as possible about the programs that we write. Okay, and essentially not let the mechanisms for getting guarantees and better properties of our programs get in the way of being able to write programs in a way that is as natural as possible. Right? The way we're going to do this, there are essentially three components to our approach. The first is called multistage programming. And essentially, this is a way to separate the design that's captured by our program from the actual implementation that comes out of the design at the end of the day. And one way to think of this is that our programs are really, our designs are going to generate the programs that we want to run at the end of the day. Okay. Another aspect, especially important for real-time and embedded systems, is to incorporate a treatment of reactivity, or a way that allows us, a mechanism that allows us to write programs naturally, where these programs would be interacting with a stream of inputs coming from the outside and producing a stream of outputs back to the environment. And finally, using advanced type system techniques, in particular linear types and index types, to be able to express much finer properties than a typical type system or a traditional type system would let us do. Okay, so the plan for the rest of the talk, we're going to start with a sort of a caricature of traditional computing called batch computing, where all the inputs are available in one shot for a computation for the program that we want to build. And the output comes only after we have all the inputs that are needed. Right? So we're going to go extend this model in one dimension, and here, what we have is some of the input arriving early, and we actually use that as soon as it arrives to do some computation and produce a new specialized computation. The specialized computation can then receive the rest of the input and produce the output more efficiently. Okay? And we can even, later, we'll see how this separation is also useful for getting stronger guarantees about the final phase of the computation. So the other almost orthogonal dimension is reactivity, and we'll talk briefly about what this means and what programs written for this model of computation would look like, and the work that was done to make sure that we have stronger guarantees about a reactive programming model. And in some sense, we're going to be combining these two approaches at the end of the day. That's essentially the ultimate goal of the research that we're doing. So in this view, we basically are able to write our programs as designs that could use arbitrary resources to synthesize the final product that we want to produce. Maybe it'll run on a small platform, maybe it'll be a real-time program that has to run as part of a bigger controller in a car, for example. And we still want to be able to get very strong guarantees before we produce this program for any particular instance. Another way of seeing this is that we want, for our design, we want to have a type system that will tell us that for any input, what we'll produce in the second stage of computation will also be guaranteed to be resource bounded, okay, before we know what the instances are. So we'll first begin by looking at multi-stage computation. What we'll do here is we'll look at a simple program written in a functional language that performs a simple computation of taking an integer n and raising a real valued number to that exponent. So we'll take a natural number n and a float, and we'll compute x to the n. The way we do this in OCaml is fairly straightforward. The code is simple. Let means we have a declaration. Rec says it's a recursive declaration. This is the name of the function we're defining and the two parameters with their type, and we're annotating the function also here with the type of the return parameter. Just as a side comment, we don't have to write these types because OCaml can infer these types for us automatically, but we've included them here for clarity. All we're going to do is we're going to say if n is equal to 0, then we're going to return the answer 1. Otherwise, if n is even, then we'll do this trick where we call the exponentiation on the n parameter divided by 2 and then square the result, right? And similarly, if n is odd, then we'll just take x and multiply it by the exponent by recursive call to x, where n is reduced by 1. So this piece of code is really simple. It's doing a fairly trivial computation, but it illustrates an interesting example of a problem where nobody would really write this kind of program if they needed to compute exponentiation. Okay, it has too much overhead. It's a generic program. It's easy to understand, but as a piece of code, normally we wouldn't write programs like this. Okay, why would we not do that? Well, for things like x to the power of 3 cubed, there are much easier ways to do them, much cheaper ways to do them than to call this function. Right? Okay. This is a problem with abstraction. How can we simply allow the programmer to write something like this and not pay the overhead for this generality every time they want to compute x to the power of 3? So the basic idea of staging is going to be to let us have a way to use this input n, if it's available early, and produce a specialized program. So essentially, the picture that we want to have is something like this, where the one computation that we had initially is split into two parts. One we want to know gets done early and be guaranteed that it gets done early. Okay, this is going to be the P1 part, and the P2 part is going to be what's left to do in the second stage. We're able to do this in a multi-stage language with some simple annotations. There are the things, the changes are the things in yellow. But first, let's look at the types. The basic idea here for statically checking multi-stage computation is not only do we say that x is a delayed value, so we're going to treat x symbolically, but we also say that x is a delayed value that's going to represent a real value in the next stage. Okay, so this is the extra information that we have here, and we know that not only are we going to produce a symbolic representation of our computation at the end, but this symbolic computation corresponds to a value of type real at the end of the day. All right, and this makes sure that we're able to guarantee that whatever generator we write here will always produce a well-typed program, and we never have to worry about free variables or, inconsistent computations in the generated program. All right, in the rest of the program, we're almost sort of like guided by the return type. We know that this is a delayed real, so all we have to do to get a delayed real out of a real is to put it in quotations, and this is what we do here. This line doesn't need to change. Also, actually, the if statement doesn't need any changes because n is still an integer, and we could do the test n equals 0 immediately in the first stage. But this gets delayed for the second stage. The real reason why we have to keep some things to the second stage is what happens here. And in particular, if you look at this line, we're going to be doing a multiplication, or we used to do a multiplication here. And what's happening is that this x that we want to use in the multiplication is now known to be delayed, meaning it's going to be coming in a later stage. Okay? So because this multiplication is delayed, to express this in our program, we quote the whole expression. Okay? This means the multiplication is not done until the next stage. To incorporate the x that is coming in as a parameter, we put this little escape in front of it, say this is a piece of code that needs to be spliced into this piece of code that we're creating here. The other really important thing is that we can also escape the quotations around this whole expression and say, well, you know what? The call to exponentiation can be done right now. This doesn't mean that we're going to get a real valued result from the call to x, because now this is the staged x. We're changing our whole program. What it means is that all of the testing, like the conditional and this other conditional, and all of the additional computation besides the multiplication is going to be done in the first stage. So in fact, this escape here means we can do the call immediately. We can also do the subtraction from n immediately, and we pass it x still as the reference to the same delayed computation for the future stage. Yes, question?
You need to do exponentiation where the power depends on your later input. Do you now have to write a second exponentiation function where both inputs are delayed?
That's a very good question. So the question is, if we have another problem, this is a particular sort of variant of the power function where we're getting this input early and this input late. The question is, what if we have this early and maybe we think we could do some work based on this, and this is the one that's late? Or we have some information mix of the information. So what we would do in the simple case is we would actually write another version with different annotations here on the types and different annotations in the code. And we would be able to use each of the two variants for different cases. In general, there's another trick, a very nice trick that we could do, which is called abstract interpretation. And that would allow us to use richer representations for these two things and do all this work ahead of time mechanically. I'll come back to this a little bit in the next example, actually. Okay. So hopefully the explanation of this was clear to everybody. If there are any questions, please go ahead and ask me now. This is done similarly, and squaring also has a similar situation to multiplication, where we don't know what the value here as a real value is going to be, so we delay the squaring operation in the same way. Okay. Now, how do we use this? Right? This just highlights what we were saying. Once we've added the staging annotations and we have a stage power function, then to use it, we could construct a little piece of code that says we're declaring a function f of x, and in the body, we're going to escape to make a call to this computation. We'll call exp with an argument of 5, exponent of 5. And notice we're passing in this symbolic value that's bound right here. Okay? One of the features of multi-stage languages is that there is never any possibility of confusion about where this is coming from. So unlike a lot of sort of like early languages where this is just a symbol, in a multi-stage language, this is actually a static index into this reference here. So there's no possibility whatsoever for confusion about where this x is coming from. There's no accidental dynamic variable capture and so on. So we evaluate this term, and this is exactly what we get back. Okay? And this is completely mechanical because the staging annotations are very much like commands in our program that tell us exactly what we need to do. There's no magic symbolic computation or simplification. It's all determined by the programmer. All right? Obviously, this is much more what we would have written by hand if we didn't have staging constructs in our language, in the sense that we're doing straight line computation for this particular problem. This is not quite, having the times 1 here is not something that we would do, but there are a lot of systematic ways to make sure that our generators don't produce this kind of thing in the first place. And of course, this is a much more efficient, and later we'll say, much more resource bounded than the first computation. Just typical examples of the kind of performance effect of staging. In the exponentiation function that we're looking at, if we compare the unstaged version with the second stage, the result of running the generation, and compare this computation to this one, speedups vary from, let's say, 5, sometimes a little bit, for other examples, lower than 5. They can range from 4 times to 40 times, depending on, for interpreter examples, if we take an interpreter and stage it, and whether we do some additional optimizations. So one thing that we often very get asked is how much of a speed up can you get from staging or from partial evaluation, which is essentially the same idea done automatically. It can really be arbitrary. All right, there's no limit to how much gain you can get, partly because partial evaluation means you're taking some of the inputs and doing the computation, and doing some of the computations. If you happen to take all of the input, well, that's still part of the input, and you could do all of the computation and you would be basically done in the first stage. Right? What's more important really to understand about staging is that it allows us to write programs that we normally wouldn't have been able to write before because the cost of abstractions would have been too high. Okay? So like the power function, the code for the power function, we wouldn't have been able to write this or a lot of other programs that are similarly very general, and we would have had to write, basically settle for writing special cases by hand because we can't generate. We don't have a clear mechanism for generating these things automatically. Okay, so this is a larger, briefly describe a larger example where we take the fast Fourier transform, which is something that a lot of times is needed in software and very often actually implemented in hardware because it's used in a lot of signal processing applications. The idea of, of this example is to see how close can we get to being able to write programs that look like the mathematical, very high-level descriptions of this computation and still be able to get implementations that are fairly efficient in terms of the low-level representation of the computation. So this is a mathematical definition of the fast Fourier transform. How can we go from something like that looks very similar to this to an actual implementation? All right, what we did is we wrote OCaml code that looks very similar to what we have here. And of course, because OCaml happens to be a functional language, it's very easy to express these things, all of these things as just parameters. And because this is a recursive definition also, it's very easy to express it just as concisely as we have here. Then we've staged it, and we decided to see how well can we do if we know the first parameter of the FFT, which is the size of the problem. All right? So there are a lot of interesting things that come up in a bigger example. So like somebody asked, what happens if we only know part of the information, or if we have different kinds of information that we know about different parts of our parameters. With the FFT example, all kinds of interesting issues came up. And the good news is that actually these are basically the main issues that ever come up when you're staging programs, and managing them is basically something that if we know how to do it for small examples, then basically that provides us with a systematic way for doing it for bigger examples. One of the first things that comes up with stage computation, or any kind of program generation technology in fact, is it's very easy to have repeated computations. And in particular, whenever we put quotations around a certain value, instead of returning a result which is like 17 or 14, a very simple value, it's very easy to write programs that produce very large values during the computation. And that can slow the generation process significantly. It can also produce very inefficient programs that repeat the computation several times. So there's a trick that was introduced to deal with this called staged memorization. And the challenging part of doing this in the generative framework is we don't want to generate code and then look at it later. Because if we generate code and that gets duplicated, if we try to first generate code with a lot of duplication and then do common sub-expression elimination, well, we've already done something that costs, that we've already generated something that's exponentially large, and then anything we do to solve that problem is going to be wasted time. So the trick is to make sure that it gets done before anything gets generated. Another thing is it's also common to see in automatically generated code simple computations, trivial computations, which just copy one value from one place to the other. Okay? Essentially, the same mechanism that's used in stage memorization can be used to deal with this problem, and it turns out to be the first instance of this idea of abstract interpretation that we could use to represent the parameters, the dynamic values that we're producing, in a way that tells us some useful information about this dynamic value ahead of time. Similarly, the same can be done for this, and you could see that if we deal with this problem, this also takes care of the output of the power example where we had x times 1 at the end. Okay, so all these problems are dealt with essentially in the same way. And finally, one really interesting thing that happened is we had used for a long time this ideal of taking something out of a math book and implementing it directly and being able to run it efficiently. And it was kind of surprising that if we took the definition of FFT as it is from a textbook and were somewhat naive about how exponentiation of complex numbers is done, then we find that we get some pretty bad round-off errors as a result. And this was something that we also noticed quickly and had to deal with. It turned out that in some ways it's related to this, but maybe not exactly the same thing. The good news about this particular approach to doing things is ultimately we found that to get really good graphs for the computations, sort of independently of the specific order in which things get done, to get the smallest number of multiplications and additions in the generated computation, we really only need a very small number of simplification operations in combination with this abstract interpretation idea. And they're fairly simple properties. So, the properties of 0 and 1 for addition and multiplication and for negative numbers, and some very simple properties of geometric functions. Okay. The first set of rules here is enough to deal with all the unnecessary computation, except the unnecessary copying, of course. And the second one is what was needed to deal with the accuracy problem. So we were able to, when we implemented this, we were able to produce the code for various sizes and compare the direct implementation, directly staged implementation, with the ones that were slightly more intelligent using abstract interpretation and so on. And we compared them to the implementations in the FFTW system and another standard way of doing FFT, which is split radix. And interestingly, it turned out that the two implementations that we had that were only different in one parameter matched very closely what FFTW and split radix does. The key insight, the very high-level insight about FFT that came out of this is, in fact, that there's a very small difference, a very tiny way to characterize exactly the difference between the FFTW way and the split radix way of doing the fast Fourier transform. And it's essentially just in the way that we define complex multiplication. Okay? So because we were able to implement this generator for FFT circuits in such a high-level way, we were able to make this observation fairly quickly. If there are two ways of defining complex multiplication, one is basically where we use 4 multiplication, and the other is where we use 3. And if you switch from one implementation to the other, you move from FFTW to split radix and vice versa. Okay. So what's the moral of this part of the story? I think to me it's saying that if we have better tools for writing generators that produce lower level implementations, and we can focus, we can keep our designs for these generators small, we're able to see more about the problem that we're solving, right? And we get very high level insights into the kind of computation that we're doing. All right, so now to the reactive dimension of going from batch computation to something much more sophisticated. Here's what an FRP, function reactive programming program. This is an extension of functional programming to deal with reactivity. Here's what a simple FRP program looks like. There are going to be two concepts of interest. One is continuous behaviors. These are values that are outside the computer in the real world and that are changing over time. And here's one way to define them inside our program. So you're going to say the value chase mouse is equal to move by some offset the picture of Becky, where offset is initially integral of this value velocity, and velocity itself is equal to the mouse coordinate, the location of this mouse, minus the offset that we've defined here. Okay. This syntax, by the way, this is an actual Haskell program. Haskell is another functional programming language. And the behavior that we're going to get from this complete specification is when we move the mouse, value of offset changes, and we get the picture to move. The picture gets to follow the movement of the mouse. Okay. So the idea is continuous behavior. We can also incorporate discrete behavior and reaction to discrete behavior in a similar way. We define the value grow flower to be stretched by some size, the picture of the flower, where size is initially 1, and then it's going to be the integral of this b sign, another value called b sign. What's b sign? Well, initially b sign is going to be 0. It's going to stay 0 until we get an event happening on the outside. If this event is the left button press, the value changes from 0 to -1. So this means, of course, that the integral is going to be starting to go down over time. Okay. And the b sign is going to be -1 until the left button is released, in which case we go back to b sign. That means that we go back to the initial state in which we were in. Another thing that could happen is if the right button is pressed, well, instead of -1, we'll have the value 1, and then we'll do the same, essentially the analogous thing for the other side. All right. So again, this gives us a complete running program, and the way it's going to work is whenever we get left button pressed, size is going to go down, and the right button is pressed, size is going to increase. Okay. So these two slides illustrate the basic ideas in function reactive programming, continuous behavior, and discrete events. And the FRP framework has been used to program all kinds of applications, including graphics, animations, and programming robotics systems, and a whole bunch of different really neat applications. Now, FRP allows us to express reactive computations pretty nicely, but it's done in the middle of a complete functional programming language, which means among other things, for example, it has garbage collection. Well, garbage collection is really wonderful when we're not doing real-time programming, but when we're doing real-time programming, this means that in any time during the computation, we might have to wait until the computation is finished with garbage collection. So what we did with FRP is we extended it, actually we cut it down to a much smaller core, which allows us to express the same kinds of computations that we were describing in the previous two slides, but without having the rest of this big functional programming language around. So we don't have access to all the other cool things that we can do in Haskell, but we're able to write the reactive programs much more directly. And this way we're able to get much stronger guarantees about the computation that we were able to get with Haskell. So it was used to program, a little robot, for example, this guy has a little radio receiver and 2 small wheels, and each one of them is connected to a motor. And it comes with, and it uses a PIC microcontroller that uses a certain subset of C to be programmed. To look at a simplified part of what is involved in programming this little robot, we have the wheel here and the motor, and it's our job to send the right signals to the motor, right amount of power, to get a particular desired speed. All right. So the way we'll do that is we'll get ticks from some kind of infrared counter on the wheels, and based on that and another slow clock from the outside, we're going to determine what the actual speed is, or an estimate of the actual speed. From the radio, we're going to get signals to increase the speed or decrease the speed, and based on that, we're going to determine what the current desired speed is. Look at the difference between them, and using another external counter, we're going to determine how much power to send to this motor. So this is the EFRP code for doing this. We'll define the desired speed. For each one of these boxes, actually, we're going to have an equation in the EFRP language. Desired speed, we're going to say, is initially 0, and on an increment speed signal, the desired speed becomes desired speed plus 1. If we get a decrement speed signal, we decrement it, and similarly, we define the actual sort of speed estimate, which is going to be based on counting the number of ticks we get from the infrared sensor until we get a slow clock signal, and so on. Okay, so this is the EFRP code for this controller. The implementation takes the EFRP code, translates it into this event handler style C code. The two main things that I want to say about this code is, on this side, any program that we write, we're guaranteed that it's going to be terminating and it's going to be using a finite amount of space. And of course, we can't in general say this about C code that we write by hand. It's very easy to write a one-line program that goes into an infinite loop, for example. The other thing is, from the point of view of designing these kinds of programs, a lot of times we're interested in what happens to a particular piece of the state, such as speed. How is this particular piece of the state determined? And in this representation, we get everything that relates to this value in one place, in the C part, this gets scattered in different parts of the computation that have to do with how to react to different events. Okay. Now, having said that, this localizes certain information that we might be interested in. When we're looking at the real-time behavior and we want to compute the bounds on how much time is computed to react to a particular event, of course, this also has useful information because it lists all the work that we have to do to respond to a particular event. Most recently, we've been taking the work on EFRP and extending it to be able to write device drivers. And one of the main things that we did there is to extend EFRP. First, we made EFRP by cutting down FRP itself. And the main thing that we've been doing recently is extending FRP with extending it carefully with features that would allow us to not change the input-output semantics and our ability to reason about EFRP, but to change the kinds of resource guarantees, the real-time guarantees that we get. So with a priority scheme, for example, that's transparent and that works transactionally, we would still be able to read our programs in the same way that we did before, even though what may happen in practice is some event might occur, we might start handling it, and then another one with a higher priority might interrupt it. We would throw away the work we were doing, attend to the second one, and then get back and deal with the first one later. Okay? So that's the kind of thing that we've been doing mostly to deal with the device driver example. Okay, so finally, when we combine these two things, what benefits do we get, and what is the technology that's available to be able to do this kind of thing? So to give you sort of like an intuition for what we want to do, here's yet another example, a very high-level computation, high-level description of a computation sorting. And here we've defined it with two recursive functions. One is insert and the other is sort. And this is sort of a classic insert sort function written in a functional language. We define sort as saying, let's look at the list L. If the list is empty, the sorted list is just the empty list. Otherwise, all we're going to do is we're going to take the first element in the list and insert it in the right place in the sorted version of the rest of the list. Okay? And insertion itself is going to say, let's take an element and a list, and how do we return something that has the A in the right place in the L? We'll look at the L. If the list is empty, then it's obvious we just return a list of size 1 that carries this element. Otherwise, what we're going to do is we're going to look at the list and see if the head of the list is greater than the element. If our element that we want to insert in the right order is smaller than the head of the list, then we're simply going to put the new element at the beginning and then basically return the rest unchanged. Otherwise, what we have to do is we have to put the head of the list at the beginning and insert A in the right place in the rest of the list. The very high-level description for how insert sort works. The unfortunate thing about it is, we'd probably never want to implement insert sort this way because it's not resource bounded. In fact, it takes much more space than we would normally need for sorting a list. So a really cool thing that was done a few years ago by Martin Hoffman and company is to produce a functional language, high-level language from our point of view that has a lot of the nice abstractions. And what it does, it has these linear types. The linear types allow us to guarantee that essentially, with very small change on the previous program, we can annotate it with typing information that says, you don't actually have to do any mallocs to do insert sort. Okay? You can do insert sort without any allocation of additional memory. How does this work? Well, maybe we'll get an idea if we look at how the type system works. The essential idea is that in addition to any kind of dynamic constructor, we're going to say that the type system needs to know have some abstract understanding of where this structure is stored. Okay? So this is going to be almost like a capability that comes when we deconstruct or analyze a list. So if we find out that the list is a cons cell, then we also get a capability for being able to use this cons cell later. When we call insert, we have to pass a capability that would allow us to essentially find a place to put A into a list when we're returning the result. And what we'll do if the list is empty, then we'll do this cons at the same place that we got from this parameter that in the first case we got, of course, from this call. So essentially, as we deconstruct the old list, we get information about where to construct the new list. Right? And a similar thing happens when we're pattern matching on the rest of the list here. When we're finding out that this L is a cons, we get this capability that we get to use at this point to create this cons cell. And for this cons cell, we could use this one. Of course, we could have interchanged this D and E. But the type system makes sure that we can't use any of them more than once. That's why it's called linear, is because any of these capabilities can only be used exactly once. So we could exchange these two things, and we have a choice in where we do the cons. But we can only do a cons if we have a capability to do a cons, and a capability can only be used once. Similarly, we use the D and E here in this other branch, and in this case we use it directly for a cons, but in this case we use it to be able to call insert, which we know is going to malloc a cons cell. One last thing to say about this, of course, is I said E can only be used once. You know, it's introduced here and is used here. If we have an if branch, we should take into account that only one of the if branches is used. So we're able to actually use it in once in each of the two branches.
How do you know that it does refer to the old cell after you've replaced it already?
So you don't need to know exactly the identity of the cell, right? But you need to know that there is some cell that has disappeared that you could use. At the level of the type system, at the level of the implementation, you actually do need to know something about where it's going to go.
No, what I meant is, how do you know that you don't have some other variable somewhere else in the function, or maybe in another thread which is also referring to the same cons cell which you just...
Excellent question. This goes back to, yes, absolutely, thank you. The question is, how do I know that there is no other thread or other reference to this thing that somebody else could be using at the same time, right? So we said that the core idea here in this language is linearity, and linearity is what's going to allow us to type check this program and make sure that it can be implemented with any additional mallocs. How do we know that nobody else has a handle on this? This is an excellent question. Goes back to my very first slide. The abstractions that are used in the language interact very directly with what we can do to make guarantees about the programs written in the language. If we have multi-threading, and if we have other ways to store references to this cons cell and the capability, then we wouldn't be able to get this guarantee. Okay? It wouldn't necessarily work in the direct way. So this doesn't mean also that we can't have multi-threading in these languages. It just means that the direct way to incorporating multi-threading would indeed violate the property that we're trying to establish with the type system here. So I haven't thought about how to deal with that particular interaction, but it would be a very good one to.
So if you want,
it's a very good one to consider.
You must have some kind of somewhere in the type there must be an annotation whether you have exclusive access to the thing or not.
That's right. That's right. And in fact, the kinds of type systems, in some ways, that one uses to guarantee properties about multi-threaded programs statically are similar to the kinds of type systems that are used here. And also index types, which I'll talk about next, are another way that people have tried to deal with threading systematically. Okay. So one does have to look at what's all the machinery that's needed to incorporate all these properties and guarantees in the same language. Yes, another question from the back.
You don't need multi-threading to have problems here. You just say L equals sort, or the test L equals sort L. So you, I guess, have to have L be in the parameter sort.
You still be like aliasing problems?
If you call...
Yeah, aliasing, that's right. If you have any way to copy the E, you would run into problems.
Any way to copy the L, that's a parameter.
And any way to copy a structure that contains the E, you would also have problems. That's right. So the type system makes sure that not only is the E linear, but all of these data structures are also linear. Okay? So that's a slightly easier one to deal with. And in fact, there are also variants after Hoffman's language, which has been around for a while. There's another sort of step forward from linear types, which is called alias types. Right? And it deals with various other kinds of data structures and kinds of computations that you want to have around a little bit more naturally maybe than what the vanilla linear types do. Okay? And in fact, to deal with the problem that we addressed here, you have to deal with the specific problem that you mentioned about the linearity of L. Okay, so here's an example of a guarantee that we can get with a carefully designed abstraction, a more expressive type system like linear types. But one of the things that we lose with the original proposal here of linear types is the ability to pass around functions. So we forget sometimes that, functional languages are great because higher order functions are very convenient. What are higher order functions useful for? Well, especially when we're sorting, we generally want to make our implementation of sorting parameterized by things like this. We don't want to pin down the comparison operation, right? And parameterizing by something like this is essentially is done either by a callback or by passing in a function argument, all right? To get the guarantees here, we've lost the ability to pass these things as values. What do? The key idea that's done here is to develop an extension that incorporates both staging and linear types. Then we can make a very clear distinction about when this part of the computation gets done. If we think of the idea of picking the particular sort function as an earlier stage, okay, then we can use these brackets around the beginning of our implementation of insert and sort, and say that we're picking the particular implementation of the comparison in an earlier stage, and we plug it here as part of this template. The template can be an actual template where we produce completely separate code for different implementations, or it could be a virtual template that implements everything in the same place. All right? But by doing this extension where we make the staging distinction explicit, we're able to recover back the expressivity of the higher order functions so that we don't have to write source code for exactly the same thing several times. We're still able to do it in a parametric way, and also keep the guarantees about being able to do these modifications in place for the computation of the insert sort. Okay, and a lot of the work actually that has to do with being able to get this extension of the linear type system has to do with making sure how can we write a language where we're able to copy things that are safe to copy and not copy things that and make sure that things that can't be copied are not copied. Okay, so this was linear types. The other thing that I'd like to sort of briefly mention today, that's another really important component of resource-aware programming, is index types. Okay, here's the intuition for what index types are about. This is a type declaration in OCaml that doesn't use index types. So we'll go over this first quickly to make sure that the syntax is clear. We're declaring a type for list parameterized by type parameter A, and the list can be either nil or a cons, which carries a value of type A. So if A is int, then we would have an int right there. If A is a string, we'd have a string right there. And the other part, the tail of the list, is itself a list, and it also has to be parameterized by the same A. So this is a simple polymorphic list, and the append function described here simply says we're going to take two parameters. One is called x's, and the other is called y's. The s's are typical for referring to lists in functional languages. Both have type A list, and the return result is of type A list as well. The way we do append is if the first argument is empty, then we just return the second argument. That's the easy case. Otherwise, what we do is we break down the first argument into the head and the tail, and we put back the head on the result of appending the tail of the first one with the second one. Is this clear to everybody? Okay, so fairly standard definition, just making sure that the syntax is clear. What we're able to do with index types is not only to have a data structure that says this is an alpha list, and this list can only carry things of type alpha, meaning if we pick alpha to be int, they're always going to be ints. It's a homogeneous data structure and so on. What we're able to do with index types is to say much more precise information about the data type, the data structure. In fact, we can pin the data structure to its exact value using this mechanism if we want to. But that's not always necessary. So what we'll do in this example is to say, we're interested in lists, polymorphically typed lists, and we're interested in knowing ahead of time what their size is. This is exactly the same problem that we'll have with arrays if we wanted to ensure that array bounds checking is done statically, for example. So what we do here is we add an extra parameter called, in this case, n. It's not your everyday type, but it's an index type. And what that means is we can actually write functions that work on these types. So it's going to be of type. The type is called nat. Or the kind of the type is called nat. So the type of the type is a natural number. Now we say that nil which we knew before is an alpha list of size 0. So this parameter here is restricted to be of size 0 if the value is nil. And then in the next case, what we want to say really is a cons value, if it's carrying a list of size m, then the whole thing is of size m plus 1, or successor of m in this case. Okay? And we're able to do this by declaring this local m, which is a polymorphic parameter that's going to range over the value that's carried by the cons cell and the cons cell itself. Is everybody clear? Are any questions about this one so far? All right. With this additional structure in the types, what we do is we're able to go to append and essentially say that it has the following type. If the first argument is of size m, the second argument is of size n, then the result is going to be of size m plus n. And this is going to be all statically checked. To do that, we're going to take two parameters. The first one is the size of the list as arguments to append. The first list, the second one is the size of the second list. And in slightly more elaborately type-decorated match statement that refers to what the size of x is, type of x's is, and what the type of the return value is going to be, we're able to say the code here stays the same. Here, when we do the analysis on the cons cell, we want somebody to tell us what the value of this m is for the particular argument. We take this value, and then we're going to construct a new cons cell where we say the size of the new cons cell is going to be m2 plus n, where n is this parameter. And what we carry is exactly the same as before, but we also pass in to append the size of the rest of the list. Okay? And this is all statically checked, and now we know that whenever we use this append function, we're guaranteed that the sizes of the parameters are going to be known statically. And it's going to be safe to assume that these are the sizes. Okay, what is cool about index types done this way? This is actually, the last slide was something that we just presented a paper about in Nice last week at PEPM 2007. All the checking of the types is done statically. Nothing is left until runtime in the static type. So they behave exactly the same as before. Basically, any program that you know is safe and that you could prove to me that is safe, you could type check.
So you've solved the halting problem?
No, I haven't. Okay? So the key thing is that any program that you know is safe and you could prove to me is safe, you could type check. Okay? So the key is actually in having the proof. So if you have the proof, you could plug it in to the type system, and the type system can incorporate this proof directly.
How would you express the proof of Fermat's theorem in your programming language?
If you have the proof, you can do it. If you don't have the proof, you can't do it. I'm sorry. All right?
Yeah, I mean, you need concepts from higher math which might not be expressed.
Yes. So it's not necessarily going to be easy that anything you have a warm, fuzzy feeling about that it's true, that you're going to be able to explain it to the type checker. But for the more sophisticated library building programmer that knows that certain properties hold about these libraries and they can actually demonstrate it, then they're able to express these properties now. Okay? So not everybody can type check all the programs that they would like to type check, but a sufficiently skilled programmer is going to be able, now has a way to communicate this information to the type checker. All right? Yes?
So what's the underlying logic?
Excellent question. The question is, what is the underlying logic for this framework? The name of the language that we just released is Concoction, and the middle part is COQ. This is in reference to the Coq proof checker from France. So it's higher order logic, the calculus of inductive constructions. And they have things like formalisms of the real analysis results. There's an 8 megabyte proof library that where they've machine checked the key results like the fundamental theorem of calculus and stuff like that, written in Coq. And very, very expressive proof language. And what it'll do for you is you write the proof, it'll check it. It's not a, you could use it kind of as a theorem proving framework, but it's primarily a proof checking framework. And this is, in the last example, this is actually what's used to write all these types. Whenever you see a tick paren, tick paren, tick paren, all of these things are actually terms in the proof language. And all of the checking on these things is done by the proof checker. Okay? Yes, another question?
If I want to write append in the way you just did, but I don't want to prove that, say, sort produces the right size list yet, can I pass the same type to append if I pass it?
Coercions are tricky. So this is another talk about gradual typing for higher order types. And the question, let me repeat it, sorry. The question is, if I wanted to write my regular sort, which doesn't have the information about the sizes in the type, and I wanted to use it in conjunction with this append, what do I do? Can I simply do a cast? The short answer is basically this is a combination, what you're looking for is a combination of gradual typing and the more expressive types that you get from index typing, still ongoing work. It's not possible to get soundness, it's not possible to do it without actually checking the size of the list. Okay, so I think for this particular example, the least amount of work that you could do is dynamically look at the list, see how many elements you are, and then construct a list, a size that says, okay, there exists a size for which this is a sized list, and here's the size. That's basically the least amount of information that can be done. In terms of applications, basically we can guarantee any property that we know how to verify ourselves statically, and it'll be checked by the machine. And of particular interest is DSL implementations, and to be able to check DSLs statically, check the type systems and the parsing statically for DSLs. So in summary, the key ideas behind our work on resource-aware programming are to capture the design intent very clearly in the code that people write for embedded and real-time systems. At the same time, to have solid guarantees about low-level properties, in general resources that are used in the computation, and to make sure at the same time we have the expressivity and we have the low-level control, but safety is not violated, right? So these things are integrated together soundly. The key ideas that are used to realize this are multi-stage programming, index types, and reactivity. These are the things that we talked about, gave examples of in the talk. And ultimately, this should make programmers more productive and make their life easier, make it easier to produce better, more reliable programs. And thank you very much, and I'll leave these things up as pointers to further material if you're interested. Thank you. So we're a little bit past time. I don't know if we have any more time for questions.
Yeah, I think we're done now. So it doesn't look like anyone's clamoring to get into the room, and so I don't think we're going to be rushing off. So if you have questions to ask, you can come up and do that. But otherwise, we're all finished with the talk. Thanks.
Very good. Yes.
So where does this not work?
So right now, that's a very good question. The question is, where does this not work? Right now, we just finished the release of Concoction, which has the support for the index types. We haven't written a lot of programs in Concoction yet. There are a lot of programs that we would really like to write in Concoction. In fact, we've created this language because we had a lot of programs that we needed it for. But right now, we're at this point where we've just finished the implementation. It's released. It's available online. The manual is extremely short. It's 4 pages because all you need to know is OCaml and three other constructs to start programming in it. But what I'd like to do next, what we would like to do next is to get much more experience with programming in this language with index types. And in fact, while there are a lot of related systems that are out there, there's a lot of interest in index types in the programming languages research community. There aren't a lot of distinct program examples that we know of. There are a few small ones that are used to compare languages, but I don't think that there is a large body of programs in languages that have index types yet. So we're very excited about actually trying it out and see if it can do all the things that we would like to do. The other thing that I think is very interesting is what was pointed to earlier with the question about what if I have an old kind of legacy function like sort with the old type and I want to integrate it in this framework. And recently we've put forth a proposal on gradual typing. And the idea is that this would provide the machinery needed to have part of the program that have old types that don't tell us very much, or even no types like Scheme or dynamically typed languages like Python, for example. We're using Python now as an example, for what we would like to do, and be able to integrate that with extensions of the language that have types and that do have guarantees about the type parts. So that's kind of another area where we'd like to go. Yes?
How do abstractions and APIs look, or APIs of interfaces between components look like in this system for kind of real world kinds of things. Yes, that playing with lists, sorting, it's a little number work is fairly easy to describe completely what it does, but when you get to larger things, windowing systems or real-world applications, the description of an interface would leak so much information about what's going on inside.
Oh yeah. So the question is, how do real-world components, fit into this model of the world? One of the things that could happen is, if you describe with index types, you can say factorial has type, it takes an x and returns factorial of x. So you're no longer say it takes an int and returns an int, but it takes a particular x, give me whatever x you want, and I'll produce a number which is specifically factorial of x, which is fact now is defined in the type. You can specify your full input-output behavior in the type, okay? And for some things, that could be a good thing. You could use this. This means that you could use it for some kind of verification if you want. I'm personally not particularly interested in going that far with index types. I'm much more interested in things like the append, for example. But you're not necessarily, even if you do that, I mean, first of all, it's a choice. It's up to you whether you want to use the index types there or not on larger components. If you do that, you'd only be able to capture the input-output behavior and not necessarily the side effects and the implementation details, okay? So if you just use the types as they are in OCaml now, there's still a lot that you can hide. In fact, there's still a lot that you can't capture explicitly in the type. So ultimately, I think this is again a situation where, to start exploring this world, to start exploring what can be done usefully with index types there, and what may be disadvantage of index types, we have to try these things and see what happens. And a very good tool for being able to explore that, in addition to showing Christmas party pictures, is to have a mechanism for gradual typing that would let us have components from old types and new types live together happily. Right now, you can have both of them in the same language, but you can't use both of them very easily together. There's a reference to a paper on stage programming that has 20 different ways of staging one function. I suspect it was an interpreter, that paper, not the factorial function. Or is it a specific paper that you have in mind, or is this a hypothetical paper?
Probably introduction to mental panel or something like that.
Okay, so I think I know the paper that you're describing. So in that paper, there are about 10 different versions of an interpreter done for a progressively more expressive language, so it's not exactly the same language. And the idea of doing it in 10 different ways is really to explain to people reading the paper how to write interpreters for more sophisticated languages. So that's kind of the reason why there are 20 different versions there. And ultimately, when one is writing an interpreter for sophisticated language, you have to do a lot of experiments. It's not just something that you sit down and do. But I think what you're really asking about is, if I have a lot of variability in the times at which different inputs arrive, like for example in the power example, one input might be arriving early and the other late, but then you might have a situation where they're different, right? And you're concerned about how do we do things when that happens. The general way of doing things that seems to work is this abstract interpretation trick, where you basically have a slightly more interesting data structure for both of the inputs. And then you say, okay, here's what I do when the first one is available early, and here's what I do when the second one is available, early, and so on. So there are ways to manage them. I don't think that right now I could claim that there is a perfect solution for this problem. This is an issue that has been around for a long time. In fact, it was fairly well known in the partial evaluation literature, which kind of produced multistage programming. Multistage programming solves certain problems that arise in partial evaluation, and in particular being able to control exactly what the partial evaluation is doing. But this issue is still kind of an open issue. And now, especially with the index types, we're able to do much more informative experiments than we were able to do before. Because unfortunately, we also ran into this problem of, types can get in the way. When the type system is too simple, then the types can actually prevent you from writing programs that you'd really like to be able to express. And especially for this application area of statically checked domain-specific languages, which is almost any language that you're interested in, with the exception of some dynamically typed languages. Almost any language has some typing structure. If you want to interpret that and write a staged interpreter to implement it, then you have to deal with this limitation on typing, and index types really help us with this. Okay. Remember, actually, in the very much earlier on, the speed up from interpreters was somewhere between 4 times and 44 times. The difference between them is whether you're able to use index types or not. So index types in that case give you a factor of 10 speed up, whereas staging just gives you a factor of 4. Okay. So the being able to write index programs now is very important to make the next step. Yep. FFT. Yep.
It seems that in a general case, if it's pretty pertaining to Fourier transform, then you'd end up with like a general technical system or something. Not irreconcilable. Because you're relying on those simplifications.
Right. So the question is, in the FFT example, we had these rewrites. I didn't really say very much about how they're integrated into the implementation, but being able to use these writes is essential for producing the code that we get at the end. And the question is, well, in general, how many rewrites do we need to have? In general, you would need a lot of rewrites to solve all problems, nicely. The reason why these rewrites and the fact that they're small is very useful for this particular example is a lot of times, to be able to write good generators for certain applications, we need to be able to incorporate domain-specific optimizations or problem-specific optimizations. So the idea of that example is when you're writing a generator, it makes a lot of sense to be able to somehow be able to incorporate these optimizations that are specific to the problem. With this abstract interpretation technique, I didn't talk about how you do the details here, but with the abstract interpretation technique, you actually have a fairly systematic way of taking the data structures that you're working with and incorporating these rewrites on these data structures so that they're performed during the generation process. The issue of how you direct them and how you make sure that they're actually usable effectively as opposed to diverging and going into an infinite loop themselves is addressed in that context. Basically, it's the responsibility of the person developing the staged implementation to sort out how to direct these rules and how to produce an implementation based on these rules. So there's no black box where you put in the rewrites or the equalities and you get the rewrites out. That's outside of the basic programming framework. Absolutely, absolutely. Absolutely. So it's the programmer, the designer, the person designing whoever is designing the implementation of FFT needs to know enough about what are the essential optimizations that are needed here, and they're given a particular method for turning this into fairly easy to read code that does what you want. But right now, there's no toolbox for writing the equations and deriving the rewrites from. Okay. Actually, the question back here.
So the title says something about bounding the resources with types. Do you have a way yet to say, like, this function allocates no more than a meg of memory or runs in 3 milliseconds?
So we haven't actually ourselves done these kinds of very specific experiments on specific programs running on specific platforms. But there are other results in the literature where people have done that using essentially the same mechanisms that we now have in the framework. So with index types, there's a very nice paper from a few years ago by Carl Crary and Stephanie Weirish on using index types to talk about, I think the number of time steps. And I think there are also concrete studies on size as well. Right? And the motivation at the beginning was to say, what are the mechanisms that we really need to have in our language that would let us talk about all of these resources. And the quantification that we get with the index types now is the essential thing that wasn't there before.
How do you prove anything non-trivial about programs that deal with floating points? It's not associative, it's not distributive.
We haven't done any experiments in that direction yet, but there are some very interesting libraries that formalize. So the question is again, sorry, how do we prove anything about floating points in this framework? And there are some very nice theories that formalize fixed point arithmetic in Coq now. We haven't used them yet because we've just finished the integration of the Coq mechanism into the types, but we certainly would like to be able, we expect to be doing work with these in the near future. So hopefully in a month or two, I'll be able to say more about that. Any other questions? All right, thank you very much.